A 200,000 light-year streak of newborn stars forces a specific question. What kind of object can drive a bow shock at 1,000 kilometers per second through the gas surrounding a galaxy and leave a trail of star formation in its wake? The answer, according to a team led by Peter van Dokkum using Hubble Space Telescope imaging and Keck Observatory spectroscopy in 2023, and confirmed with NASA's James Webb Space Telescope infrared spectroscopy in 2025, is a runaway supermassive black hole, a massive compact object ejected from its host galaxy's nucleus during a multi-body gravitational encounter, now plowing through circumgalactic gas at supersonic speed. Galaxy mergers, the gravitational encounters that build the largest structures in the observable universe, can produce triple supermassive black hole systems, and three-body gravitational slingshots in these systems can eject one black hole while the remaining pair tightens and merges. Gravitational-wave recoil, the linear momentum kick imparted to a merger remnant by anisotropic gravitational wave emission as demonstrated by LIGO-Virgo detections of stellar mass black hole mergers at smaller scales, provides a second ejection mechanism, with numerical relativity calculations by Carlos Lusto and Josef Zlochawa demonstrating that recoil velocities can approach 5,000 kilometers per second in certain spin configurations. Meanwhile, astrometric microlensing, the detection of dark, compact objects through the gravitational deflection of background starlight, is revealing isolated stellar mass black holes drifting through the Milky Way, invisible except for the light they bend. And the optical gravitational lensing experiment, OGLE, has spent 2 decades monitoring tens of millions of stars toward the Large Magellanic Cloud, producing the strongest constraints on primordial black holes as a dark matter component by detecting nothing where massive halo lenses should have appeared. What follows is a forensic examination of the evidence. By the end of this video, you will understand how galaxy mergers produce the conditions for black hole ejection. You will understand the physics of three-body slingshots and gravitational wave recoil kicks. You will understand what the 200,000 light-year streak actually shows, and why a competing interpretation argues it may be something far more mundane. You will understand how astrometric microlensing weighs invisible objects using nothing but positional drift. And you will understand the current constraints on how many rogue black holes could be drifting through galactic halos, and why the strongest evidence sometimes comes from decades of observing nothing. If this channel is the kind of content you return to, consider subscribing. There is no algorithm shortcut for depth. Let us begin with the streak. In deep Hubble Space Telescope imaging, processed through the Advanced Camera for Surveys, an instrument installed on Hubble in March 2002 that replaced the faint object camera and dramatically expanded Hubble's wide-field imaging capability, a thin linear feature appeared at a redshift of approximately 0.964. The redshift places the object at a look-back time of roughly 7.5 billion years. We are seeing the feature as it appeared when the universe was approximately half its current age. The feature extends roughly 62 kiloparsecs, approximately 200,000 light-years, or about 1.89 times 10 to the 18 kilometers, roughly 1.18 times 10 to the 18 miles. 200,000 light-years. For comparison, the diameter of the Milky Way's stellar disk is approximately 100,000 light-years. The streak is twice the diameter of our entire galaxy. It is narrow, far narrower than a typical galaxy, and it is straight, maintaining a linear trajectory over its entire 200,000 light-year length with no measurable curvature or deviation. The feature is aligned with a nearby galaxy, terminating in a bright knot of ionized oxygen emission, a concentration of doubly ionized oxygen, the spectral signature known as the forbidden oxygen 3 line, commonly used as a diagnostic of shock-heated gas and star-forming regions. The discovery was not accidental in the usual sense, but it was unexpected. The feature appeared in archival Hubble imaging that was being examined for other purposes. Its morphology, thin, straight, terminating in a bright point, was unlike any known class of astrophysical object. It did not resemble a tidal tail from a galaxy interaction, which would be curved. It did not resemble a jet from an active galactic nucleus, which would show radio emission and relativistic physics. It did not resemble a filament of the cosmic web, which would be far larger and more diffuse. The feature was, in observational terms, unprecedented. Peter van Dokkum and collaborators, using follow-up spectroscopy from the Low-Resolution Imaging Spectrometer, LRIS, on the W.M. Keck Observatory's 10-meter telescope on Mauna Kea, Hawaii, analyzed the emission line ratios along the streak. LRIS provides simultaneous blue and red spectroscopy covering approximately 3,200 to 10,000 angstroms, 0.32 to 1.0 micrometers. The line ratios they measured, the ratios of oxygen-3 to Balmer series hydrogen lines, among others, showed a mixture of two signatures: fast radiative shocks and ongoing star formation. The stellar continuum, the broadband light from stars in the streak, showed colors that varied along its length. Near the tip, the stars were bluer, younger. Farther from the tip, they were redder, older. Van Dokkum's team fit this color gradient with a model in which the ejection occurred approximately 39 million years ago, with the black hole continuously triggering star formation as it moved through the circumgalactic medium, leaving progressively older stellar populations behind it. The implied velocity, approximately 1,600 kilometers per second, roughly 3.58 million miles per hour. Think about that speed. 1,600 kilometers per second. At that velocity, the distance from Earth to the Moon, approximately 384,400 kilometers, would be covered in roughly 4 minutes. The distance from Earth to the Sun, approximately 150 million kilometers, in about 26 hours. And yet, this object, moving at 1,600 kilometers per second, has been traveling for 39 million years and has produced a wake only 200,000 light-years long. The speed is enormous by human standards. The distance is enormous by galactic standards. And the time required to traverse it, 39 million years, is a small fraction of a typical galaxy's lifetime. The wake is a snapshot, not a permanent feature. It is a record of a journey still in progress. In 2025, the investigation advanced. Connor Jennings, Peter van Dokkum, Imad Pasha, and collaborators published the results of James Webb Space Telescope follow-up observations using the near-infrared spectrograph in its integral field unit mode, NIOSPEC IFU, which provides spatially resolved spectroscopy over a 3 arcsecond by 3 arcsecond region with 0.1 arcsecond by 0.1 arcsecond spatial elements, covering wavelengths from 0.6 to 5.3 micrometers. The JWST data revealed something the ground-based spectroscopy could not resolve: a sharp kinematic discontinuity at the tip of the streak. across a spatial scale of approximately 0.1 arcseconds, corresponding to roughly 1 kiloparsec at the redshift of the object. The radial velocity changes by approximately 600 kilometers per second. A velocity jump of 600 kilometers per second across 1 kiloparsec. This is the kinematic signature of a shock front, a boundary between the undisturbed circumgalactic medium ahead of the object and the shocked compressed gas behind it. The JWST team fit a shock compression model to the data, yielding a refined velocity estimate for the black hole. V sub BH equals 954 plus 110 minus 126 kilometers per second, approximately 2.13 million miles per hour, at an inclination of approximately 29 degrees to the line of sight. The velocity is lower than the initial 2023 estimate, but of the same order. The difference reflects a more constrained physical model that accounts for the shock geometry, the inclination, and the downstream velocity structure, including turbulent entrainment and mixing in the wake behind the shock front. The same paper argues, from energy conservation over the lifetime of the wake, that the black hole mass must be at least 10 to the 7th solar masses, at least 10 million solar masses, or roughly 2.0 times 10 to the 37 kilograms, approximately 4.4 times 10 to the 37 pounds. A public-facing estimate places the mass at up to 20 million solar masses. The energy required to drive a supersonic shock through circumgalactic gas for 39 million years, compressing enough material to trigger star formation along a 200,000 light-year corridor, demands a massive driver. A stellar mass black hole could not supply it. The energy budget requires a supermassive black hole. This is the part that stays with me. Not because it is exciting, because of what it implies about how common this phenomenon might be. A supermassive black hole, ejected from its host galaxy, traveling at nearly 1,000 kilometers per second through the thin gas of the circumgalactic medium, leaving a trail of shocks and newborn stars that stretches twice the diameter of the Milky Way. If this is a real phenomenon, and the JWST data provides the strongest evidence to date that it is, then the question is not whether it happens, but how often. Before we continue, the counter-narrative must be examined with the seriousness it deserves. Scientific claims of unprecedented phenomena require exceptional scrutiny, and the Runaway SMBH wake interpretation has received exactly that. Jorge Sanchez Almeida published a detailed critique arguing that the linear feature is not a runaway SMBH wake at all. Instead, Sanchez Almeida proposes that the streak is a conventional bulgeless disk galaxy seen edge-on, aligned by chance near another galaxy. The critique is grounded in specific observational comparisons. First, the kinematics. The feature shows a velocity gradient consistent with rotation, with a maximum velocity of approximately 110 kilometers per second, a value typical of a low-mass disk galaxy's rotation curve. Second, the structural properties. The length, surface brightness profile, and overall morphology are consistent with known scaling relations for edge-on spiral galaxies. The feature does not violate any standard relationship between size, luminosity, and kinematics for disk galaxies. Third, the physical plausibility. The wake scenario requires the ejected black hole to encounter circumgalactic gas of sufficient density and extent to form a 200,000 light-year stellar feature in approximately 39 million years. Conditions that Sanchez Almeida argues are unusually fine-tuned and difficult to achieve in standard circumgalactic medium models. The critique applies Occam's razor. Given that bulgeless edge-on galaxies are known objects that exist in large numbers, and that the Runaway SMBH wake is an unprecedented and physically demanding scenario, the simpler explanation should be preferred unless the data demand otherwise. The counter-narrative is substantive. It is not a dismissal, but an alternative interpretation grounded in specific observational comparisons and physical plausibility arguments. The debate illustrates a fundamental challenge in observational astrophysics. When you observe a rare or unprecedented phenomenon, how do you distinguish a genuinely new physical process from an unusual configuration of known objects? Morphology alone cannot decide. A thin, straight feature could be either a wake or an edge-on galaxy. Kinematics can help, but limited spectral sampling can be misleading, especially for rare geometries viewed at unfavorable angles. The Van Dockum team's response centers on several lines of evidence that they argue collectively favor the wake interpretation. First, the emission line diagnostics. The line ratios, the ratios of oxygen 3 to hydrogen beta, nitrogen 2 to hydrogen alpha, and other diagnostic pairs, are not typical of a normal star-forming galaxy. They show a mixture of shock excitation and star formation that is more naturally explained by a bow shock plowing through ambient gas. Second, the color gradient. The systematic variation of stellar population age along the feature, younger near the tip, older farther from the tip, is consistent with progressive star formation triggered by a moving source and difficult to explain as a property of a normal edge-on disk, which should show a roughly uniform age distribution across its length. Third, and most critically, the kinematic discontinuity at the tip revealed by JWST, a 600 km/s velocity jump across 1 kiloparsec. A conventional disk galaxy should not produce such a discontinuity. A supersonic bow shock does. The kinematic discontinuity is the strongest single piece of evidence favoring the wake interpretation. A disk galaxy produces smooth rotation, velocity changing gradually across its extent. A bow shock produces a sharp boundary, a discontinuity where pre-shock gas meets post-shock gas. The JWST data shows the discontinuity. This does not absolutely rule out all alternative explanations. There may be configurations of merging or interacting galaxies that produce sharp kinematic features, but it significantly narrows the space of viable alternatives. What would you conclude from this evidence? A linear feature 200,000 light-years long. Emission line ratios consistent with shocks and star formation. A color gradient implying progressive stellar ages. A kinematic discontinuity of 600 km/s at the tip. A competing interpretation that identifies the feature as a mundane edge-on galaxy. And a JWST follow-up that provides the sharpest kinematic evidence yet for the shock interpretation. The evidence file is thick. The verdict is contested but converging. This brings us to the physics that produces runaway supermassive black holes and why the ejection of a 10 million solar mass object from a galaxy's nucleus is not as improbable as it might seem. The mechanism begins with galaxy mergers. When two galaxies merge, a process that occurs throughout cosmic history as gravitational interactions draw galaxies together, their central supermassive black holes eventually find themselves in the same gravitational potential well. They do not merge immediately. The two black holes orbit each other, losing energy through gravitational interactions with the surrounding stars and gas, a process called dynamical friction, first formalized mathematically by Subramanian Chandrasekhar in 1943. The Chandrasekhar dynamical friction formula describes the drag force on a massive object moving through a background of lighter particles. F sub df equals -4 pi g squared m squared r rho log lambda times the velocity vector divided by v cubed, multiplied by a factor involving the error function and Gaussian terms. In this expression, m is the mass of the perturbing object, the black hole. Rho is the density of the background medium, the stars and dark matter surrounding the black hole. Log lambda is the Coulomb logarithm, a dimensionless factor that accounts for the range of gravitational interactions. And v is the speed of the black hole relative to the background medium. The drag force is proportional to m squared. More massive objects experience stronger friction, and inversely proportional to v squared, meaning faster moving objects experience weaker drag. Dynamical friction causes the two black holes to spiral inward toward the center of the merged galaxy. The inspiral can take hundreds of millions to billions of years, depending on the masses involved, the structure of the galactic nucleus, and the density of the surrounding environment. The process is not smooth. As the black holes sink through the stellar field, they scatter stars outward, ejecting them from the nuclear region, and gradually carve out a loss cone of depleted stellar orbits. The supply of stars that can interact with the binary and extract energy from it diminishes as the loss cone empties. This creates a potential stalling point, the so-called final parsec problem, where the binary has exhausted the stars that can efficiently extract its orbital energy but has not yet reached separations close enough for gravitational wave emission to drive the final inspiral. Whether binaries actually stall at this stage or find alternative mechanisms to continue shrinking through interactions with gas disks, triaxial stellar distributions, or the arrival of a third black hole, is one of the central questions in massive black hole binary dynamics. For our purposes, the key point is that the inspiral is slow. It can take hundreds of millions of years, and during that time, another galaxy merger can occur. Eventually, if the binary continues to shrink, the two black holes reach separations of parsecs to subparsecs, orbiting each other in a gravitationally bound binary, continuing to lose energy through stellar and gas interactions and eventually through gravitational wave emission as the orbit tightens further. Now suppose a third galaxy merger occurs before the existing binary has merged. A third supermassive black hole arrives in the nucleus. The system becomes a triple, three massive black holes interacting gravitationally in a compact region. Triple SMBH systems are not hypothetical. They are predicted by cosmological simulations and arise naturally whenever the in-spiral timescale of a binary is long enough that a subsequent merger delivers another black hole before the first pair coalesces. Pranav Satish, Laura Blecher, and Luke Zoltan Kelly, using the illustrious cosmological simulation, quantified how often this occurs. Their analysis identifies approximately 6% of massive black hole binaries forming triples at parsec scales. 6% of all SMBH binaries in their simulation volume reach a configuration where a third black hole is present at separations comparable to the binary. This is not a negligible fraction. In a universe where galaxy mergers are common, and they are, with major mergers occurring roughly once per billion years for Milky Way mass galaxies, 6% represents a large population of triple systems over cosmic time. The dynamics of triple systems are fundamentally different from binary dynamics. In a three-body gravitational encounter, energy can be exchanged between the components in ways that are not possible in a two-body system. The mathematical basis is the two-body specific orbital energy. Epsilon equals v squared over 2 minus gm over r, which also equals negative gm over 2a, where a is the semi-major axis of the orbit. In a binary, the total energy is conserved. The orbit can only change if external interactions with stars, gas, or gravitational waves extract or inject energy. In a triple system, internal energy transfer is possible. The three-body problem has no general closed-form solution, a mathematical fact established by Henri Poincaré in the 1890s, and the long-term behavior of triple systems is chaotic in the technical sense. Small changes in initial conditions produce dramatically different outcomes. The typical outcome of a strong three-body encounter follows a statistical pattern established by decades of numerical relativity experiments. The lightest member of the triple is preferentially ejected, flung outward at high velocity, while the heavier pair tightens its orbit. This is not a strict rule. There are configurations where a heavier member is ejected, but it is the most probable outcome across random initial conditions. The energy comes from the binary. As the binary's orbit tightens, the orbital energy decreases, becomes more negative, and the released energy is transferred to the kinetic energy of the ejected body. The binary hardens. The third body accelerates. The process is sometimes described as a gravitational slingshot, analogous to the planetary gravity assists used by spacecraft, but operating at vastly greater mass scales and velocities. The slingshot velocity depends on the mass ratio of the triple components, the hardness of the binary, and the geometry of the encounter. In the most extreme cases, tightly bound, high-mass binaries with a lower mass intruder, the ejection velocity can exceed 1,000 kilometers per second. For some configurations, simulations show ejection velocities that exceed the escape speed of even the most massive galaxies. Satish and collaborators found that including strong triple interactions changes the merger statistics significantly. In systems that form strong triples, the merger fraction increases from 40% to 69%. The triple interaction accelerates the merger of the remaining pair, but it also produces ejections. Under random spin orientation assumptions for the black holes, gravitational wave recoil dominates the ejected population. More black holes are ejected by post-merger kicks than by slingshots. But slingshots can produce the highest individual velocities. The slingshot is the cannon. The recoil is the more common pistol. Both can exceed the escape speed. Hauke Köhn and Michael Tremmel, working with the Romulus 25 cosmological simulation, provided complementary results through high-resolution N-body follow-ups of triple SMBH systems. Their analysis traced specific triple encounters to their outcomes: ejection of the lightest black hole, formation of a stable hierarchical triple, a tight binary orbited at greater distance by a third, or retention of the third on a wide orbit. The outcome depends on the nuclear density profile of the host galaxy. In galaxies with steep central density profiles, the three-body interaction is more violent and ejection is more likely. In galaxies with shallower profiles, the lightest black hole may remain bound but displaced. A wandering black hole within the halo, offset from the nucleus by kiloparsecs, neither ejected nor centered. The escape velocity from a typical massive galaxy is of order several hundred to 1,000 kilometers per second, depending on the total mass and the concentration of the dark matter halo. The escape velocity equation is straightforward. V sub ESC equals the square root of 2 gm over r. G is the gravitational constant. M is the enclosed mass within radius r. For a Milky Way mass galaxy with a halo mass of approximately 10 to the 12 solar masses, the escape velocity at the center is of order 500 to 700 kilometers per second. A slingshot that imparts a velocity exceeding this threshold sends the black hole on a trajectory out of the galaxy entirely, into the circumgalactic medium, into the intergalactic void, never to return. A slingshot that imparts a velocity just below the escape speed leaves the black hole on an extended orbit, oscillating through the halo, passing through the disk, wandering. Gravitational wave recoil provides the second ejection mechanism. When two black holes merge, the gravitational waves they emit carry away energy and angular momentum, but also linear momentum, if the emission is not perfectly symmetric. This phenomenon, first detected directly by LIGO and Virgo for stellar mass black hole mergers, scales to supermassive systems with dramatic velocity consequences. The asymmetry depends on the mass ratio and, critically, on the spin magnitudes and orientations of the merging black holes. If the spins are aligned with the orbital angular momentum and equal in magnitude, the emission is symmetric and the recoil is zero. If the spins are misaligned, particularly if one spin is in the orbital plane and partially anti-aligned with the other, the emission is asymmetric and the recoil can be enormous. Carlos Lusto and Josef Slochauer in numerical relativity simulations published in 2011 demonstrated that maximum recoil velocities can approach approximately 5,000 kilometers per second for certain spin orbit configurations, the so-called hang-up kick regime, where partial spin alignment with the orbital angular momentum delays the merger and amplifies the asymmetry of the gravitational wave emission near the point of coalescence, 5,000 kilometers per second. That exceeds the escape velocity of any known galaxy. A black hole receiving a recoil kick of 5,000 kilometers per second would be ejected from even the most massive galaxy cluster. It would become a truly intergalactic rogue, a compact object of millions to billions of solar masses, drifting through the cosmic void, accreting nothing, emitting nothing, detectable only through its gravitational influence on objects that happen to pass within its Einstein radius. The astrophysical question is not whether such kicks are physically possible. Numerical relativity demonstrates that they are, but how often the required spin configurations occur in real mergers. The spin magnitudes and orientations of merging supermassive black holes depend on their accretion histories, on the dynamics of the gas that fed them, and on the torques exerted by the galactic environment. If spins are randomly oriented, a reasonable assumption in some merger scenarios, then extreme kicks are rare but non-zero. If spins tend to align with the orbital angular momentum through gas disk interactions prior to merger, extreme kicks are suppressed. The Satish, Blecher and Kelly analysis explicitly notes that under random spin orientation assumptions, gravitational wave recoil dominates the ejected population. More black holes are ejected by post-merger kicks than by three-body slingshots. But slingshots can produce the highest individual velocities in certain configurations. The slingshot is the cannon. The recoil is the more common pistol. Both can exceed the escape speed. Both produce rogues. Future gravitational wave detectors like the Laser Interferometer Space Antenna, LISA, planned for launch in the 2030s, will enable direct detection of supermassive black hole mergers across cosmic time, providing unprecedented insight into the frequency and characteristics of the merger events that produce these recoil kicks. The interplay between these two mechanisms, slingshot and recoil, is not independent. In a triple system, a three-body slingshot can eject one black hole and accelerate the merger of the remaining pair. The post-merger recoil of that pair then produces a second potential ejection. In some simulations, the galaxy loses two of its three black holes, one to the slingshot, one to the recoil. The nucleus is left empty. The galaxy continues without a central engine. Whether such double ejection scenarios occur frequently enough to affect galaxy demographics is an active area of investigation. The JWST paper on the 200,000 light-year streak explicitly cites gravitational wave recoil as one of the long-predicted mechanisms for producing runaway supermassive black holes. The observed velocity of approximately 954 kilometers per second is well within the range of both slingshot and recoil mechanisms. The distinction between the two, whether this particular black hole was ejected by a three-body encounter or by a post-merger gravitational wave kick, cannot be determined from the wake alone. Both mechanisms produce the same observable outcome: a supermassive black hole moving at high velocity through circumgalactic gas, driving shocks and triggering star formation. There is a structural irony here that deserves attention. The theoretical community has predicted for decades that gravitational wave recoil could eject supermassive black holes from galaxies. The prediction dates to early numerical relativity work and was sharpened by the Lusto and Zlokowa calculations in 2011. The three-body slingshot mechanism has an even longer theoretical pedigree. The gravitational three-body problem has been studied since Newton. Both mechanisms are well understood in principle. Both are supported by simulations. But observational confirmation has been extraordinarily difficult because the ejected objects are designed by the physics to be faint. A supermassive black hole moving at 1,000 kilometers per second through the diffuse circumgalactic medium, where gas densities are far lower than in galactic disks, accretes at a rate far below Eddington. The Bondi-Hoyle-Littleton accretion rate scales inversely with velocity cubed. A fast-moving black hole is a dim black hole. The very physics that produces the ejection suppresses the electromagnetic signal that would reveal it. The 200,000 light-year streak is detectable precisely because the black hole happens to be moving through a region of the circumgalactic medium that is dense enough to produce observable shocks and star formation. If the same black hole had been ejected into a void, into a region of lower gas density, no wake would form, no stars would be triggered, no emission lines would be produced. The object would be a supermassive ghost, drifting through intergalactic space at nearly 1,000 kilometers per second, carrying the mass of 10 million suns, invisible to every telescope in existence. The detection is contingent on the environment, not just the ejection. For every runaway SMBH that produces a detectable wake, there may be many more that were ejected into conditions too sparse to leave any observable trace. Science can describe what happens and how it happens. But the question of why particular merger histories yield ejection rather than retention, why this specific galaxy at this specific redshift produced a runaway rather than a settled binary merger, remains a question of initial conditions and statistical branching, not of deterministic prediction. Even the most detailed simulations show model dependence and branching outcomes. The physics of three-body interactions is mechanistically described. The specific outcomes are probabilistic. This brings us to the broader question. If supermassive black holes can be ejected from galaxies, how many are wandering? The answer depends on which class of rogue black hole you are counting, and the answer varies dramatically across categories. For supermassive black holes displaced within their host halos, not ejected entirely, but offset from the galactic center, cosmological simulations provide population estimates that are larger than most intuitions would suggest. Michael Tremel and collaborators, working with the Romulus Simulation Suite, a cosmological simulation that allows black holes to move dynamically rather than being artificially pinned to halo centers, as many earlier simulations assumed, found that the mean number of wandering black holes rises roughly linearly with halo mass. In Milky Way mass halos, with total masses of approximately 10 to the 12 solar masses, the simulations predict dozens to hundreds of wandering black holes. In group-scale halos, 10 to the 13 solar masses, the numbers increase proportionally. In cluster-scale halos, the most massive gravitationally bound structures in the universe, with total masses of 10 to the 14 to 10 to the 15 solar masses. The simulations predict thousands of wandering black holes. The origin of these wanderers is, in most cases, not ejection. Most wandering black holes in the Romulus simulations originated as the central black holes of smaller satellite galaxies that were later tidally disrupted during infall into the larger system. The process is straightforward but relentless. A small galaxy containing its own central black hole falls into the gravitational potential of a larger galaxy or galaxy group. Tidal forces from the larger system strip the satellite's stars and dark matter, dispersing them into the halo of the host. The satellite galaxy is destroyed as a recognizable structure, but its central black hole, compact, dense, with a radius smaller than the solar system despite a mass of millions of solar masses, is immune to tidal disruption at these scales. The tidal forces that shred a galaxy act on length scales of kiloparsecs. The black hole occupies a scale of light minutes. The galaxy is torn apart. The black hole survives. The surviving black hole continues orbiting within the larger halo, on whatever trajectory it inherited from its disrupted host. Dynamical friction should, in principle, cause the orphaned black hole to sink toward the center of the larger system over time. But dynamical friction is not instantaneous. For lower mass black holes in extended halos, the friction timescale can exceed the age of the universe. The black hole never reaches the center. It wanders, oscillating through the halo on an elongated orbit, occasionally passing through the disk of the host galaxy, invisible in all but the most sensitive surveys. The Romulus simulations estimate that wandering black holes can represent approximately 10% of the local black hole mass budget once seed masses are counted. 10%. In a galaxy like the Milky Way, whose central black hole, Sagittarius A star, has a mass of approximately 4 million solar masses, 10% of the total black hole mass budget in wandering objects could represent tens of millions of solar masses distributed across dozens to hundreds of objects, each with masses ranging from thousands to millions of solar masses. None of them at the center, none of them accreting prominently, none of them easily detectable. A separate simulation program, Astrid, reports an even more dramatic population at earlier cosmic epochs. Astrid explicitly models the dynamical friction experienced by seed intermediate mass black holes at high redshift and finds that the friction is inefficient. The black holes do not sink to their host galaxy centers on the expected timescales. The result? At redshift approximately 2, when the universe was roughly 3.3 billion years old, large halos host several hundred per galaxy, wandering intermediate mass black holes. Several hundred per galaxy. These objects are too small and too faint to detect as active galactic nuclei in most cases. Their accretion rates are estimated at fractions of the Eddington luminosity, 10 to the negative third to 10 to the negative fifth of Eddington, making them electromagnetically faint. Only a small fraction would be detectable as hyperluminous X-ray sources. The rest are invisible. They wander because dynamical friction, the very mechanism that should bring them to the center, fails to operate efficiently in the conditions of the early universe, where halos are less concentrated and the background density profiles are shallower. The prediction: a large, invisible population of intermediate mass black holes drifting through galaxy halos, undetected by any current survey, accumulated over billions of years of galaxy assembly. The Eddington luminosity provides the scale against which these accretion rates are measured. L sub ed equals 4 pig sub pc over sigma sub t, where m sub p is the proton mass and sigma sub t is the Thomson cross-section. The Eddington luminosity is the maximum luminosity at which radiation pressure on electrons balances gravitational infall in an ionized hydrogen plasma. For a black hole accreting at the Eddington rate, the object is at its brightest. For a wandering black hole accreting at 10 to the negative fifth of Eddington, the luminosity is 100,000th of the maximum, faint enough to be invisible in most surveys. The Bondi-Hoyle-Littleton accretion rate provides a complementary perspective on why fast-moving black holes are faint. The accretion rate from a diffuse medium is given by m dot equals 4 pi g squared m squared rho divided by the quantity v squared plus c sub s squared to the 3/2 power. M is the black hole mass, rho is the ambient gas density, v is the relative velocity between the black hole and the gas, c sub s is the sound speed. The accretion rate scales inversely with velocity cubed, a black hole moving at 1,000 kilometers per second through diffuse gas accretes far less than a stationary black hole in the same medium. Ejection makes rogue black holes fast. Speed makes them dim. Dimness makes them invisible. I return to this point often, not for comfort, for clarity. The physics that produces rogue black holes, slingshots, recoil kicks, tidal disruption of satellites, inefficient dynamical friction, is the same physics that makes them undetectable by conventional means. The faster they move, the less they accrete. The less they accrete, the less they emit. The less they emit, the harder they are to find. The objects that are most dramatically produced are the ones most effectively hidden. A supermassive black hole ejected at 5,000 kilometers per second, the maximum recoil velocity from numerical relativity would accrete at a rate suppressed by a factor of roughly 125 billion compared to a stationary black hole in the same medium, following the velocity-cubed scaling of Bondi-Hoyle-Littleton accretion. At that accretion rate, the black hole would be fainter than any current or planned electromagnetic survey could detect. The ejection mechanism is a silencing mechanism. The cannon is also a muffler. For the wandering intermediate mass black holes predicted by Astrid, objects that were never ejected but merely failed to sink to their host galaxy centers, the invisibility is even more fundamental. These objects were never bright. They never accreted at high rates. They never powered luminous active galactic nuclei. They were born dim, remained dim, and will continue to be dim. Their existence is inferred from simulations, not from observations. Individual electromagnetic detections remain elusive. Only a handful of off-nuclear AGN candidates have been identified, and none are robustly confirmed as displaced black holes rather than projection effects or misidentified background sources. The sample size problem is real. The theoretical prediction is large populations, but the observational confirmation is sparse. This brings us to the detection method that can find them anyway, not through emitted light, but through bent light. Astrometric microlensing. Gravitational lensing is a prediction of general relativity, Einstein's 1915 theory of gravity as the curvature of spacetime by mass and energy. Mass curves spacetime, and curved spacetime bends the paths of photons. When a massive object passes between an observer and a distant background star, the light from the background star is deflected. If the alignment is close enough, the deflection produces multiple distorted images of the background star, images that are too close together to resolve individually for stellar mass lenses at kiloparsec distances, but whose combined brightness exceeds the unlensed brightness. This is photometric microlensing, the detection of a dark or faint foreground object through the temporary brightening of a background star as the lens transits the line of sight. The concept was proposed as a probe of halo compact objects in 1986, and the OGLE survey, based at the University of Warsaw and operating since 1992, was designed in part to exploit this technique. The key insight is that microlensing does not require the lens to emit any light. The lens can be a black hole, a neutron star, a brown dwarf, or any compact object. What matters is the mass and the geometry. The lens bends the light of the background star. The bending produces a time-dependent brightness change. The shape and duration of the brightness change encode information about the lens mass, distance, and velocity, even though the lens itself may be completely dark. The amplification is described by the point lens formula. A of u equals u squared plus 2 divided by u times the square root of u squared plus 4. A is the amplification factor, the ratio of the lensed brightness to the unlensed brightness. U is the separation between the lens and the source, measured in units of the Einstein radius, the angular scale set by the lens mass and geometry. When U is small, when the lens and source are closely aligned, the amplification is large. When U is large, when the alignment is poor, the amplification approaches 1, and the lensing effect vanishes. The peak amplification occurs at closest approach, when U is at its minimum value. The Einstein radius is the fundamental angular scale of microlensing. Theta sub e equals the square root of 4gm over c squared times d sub ls over the product d sub l times d sub s. M is the lens mass. D sub L is the distance to the lens. D sub S is the distance to the source. D sub LS is the distance between lens and source. The Einstein radius determines both the event duration and the amplitude of the lensing signal. The Einstein timescale, the characteristic duration of a microlensing event, is given by T sub E equals theta sub E divided by mu sub rel, where mu sub rel is the relative proper motion between the lens and the source. For massive lenses at kiloparsec distances, the Einstein timescale can be hundreds of days, months to years. This is why long baseline surveys are necessary for detecting dark lenses. The events are slow, and only surveys that monitor the same fields for years or decades have the temporal baseline to detect them. Astrometric microlensing, AML, goes beyond photometric amplification. Instead of measuring brightness changes, AML measures positional shifts. When a dark lens passes near a background star, the centroid of the lensed image shifts. The apparent position of the star moves. The centroid shift is given by delta theta of u equals u over the quantity u squared plus 2 times theta sub e. The maximum shift occurs at u equals the square root of 2, where delta theta sub max equals theta sub e, divided by the square root of 8. For a 10 solar mass black hole at 1 kiloparsec distance, the Einstein radius is of order 1 milliarc second, and the maximum centroid shift is of order a few tenths of a milliarc second, within the measurement precision of the European Space Agency's Gaia satellite. Gaia, launched on December 19, 2013, and operated for science observations through January 15, 2025, is a space-based astrometric mission that has measured the positions, motions, and parallaxes of over 1 billion stars with unprecedented precision. The satellite orbits the Sun-Earth Lagrange point, L2, approximately 1.5 million kilometers from Earth, where it scans the sky continuously with 2 telescopes separated by a fixed angle of 106.5 degrees. The scanning pattern covers the entire sky multiple times over the mission lifetime, providing repeated measurements of each star's position, measurements precise enough for bright stars to detect the sub-milliarc second positional shifts produced by gravitational lensing. Gaia Data Release 3, published on June 13, 2022, provides the catalogue that underpins current astrometric microlensing predictions and analyses. DR3 contains positions, parallaxes, and proper motions for approximately 1.46 billion sources, along with radial velocities for roughly 33 million stars and astrophysical parameters for hundreds of millions more. The astrometric precision reaches approximately 20 to 30 microarc seconds for bright stars, a precision sufficient to detect the centroid shifts produced by stellar mass black holes at kiloparsec distances. Upcoming releases will extend this capability significantly. Data Release 4, expected December 2026, according to ESA's official schedule, will roughly double the time baseline relative to DR3, improving astrometric solutions, especially for long-period signals like those produced by slow-moving or distant lenses. Data Release 5, not expected before the end of 2030, will incorporate the full mission dataset and should provide the most complete astrometric microlensing catalogue achievable with this mission. Each additional year of baseline improves the ability to detect and characterize long-duration AML events, the very events most likely to be produced by massive dark lenses. The Gaia Alert System, a near real-time photometric monitoring program that flags transient events detected during Gaia's scans, has already identified candidate microlensing events, including Gaia 18AJZ. The alert system enables rapid follow-up with ground-based telescopes, allowing spectroscopic and photometric monitoring that supplements Gaia's relatively sparse temporal sampling. For long-duration events lasting hundreds of days, Gaia's scanning cadence provides enough data points to constrain the light curve shape while ground-based follow-up fills in the gaps. Kay Howell and Lukasz Wierzykowski analyzed a specific Gaia microlensing event, Gaia 18AJZ, a long timescale event identified by the Gaia Alert System. The event was flagged as a transient brightening in Gaia's photometric time series, and its slow, symmetric light curve shape was consistent with a gravitational microlensing event rather than an intrinsic stellar variability event. The Einstein timescale, the characteristic duration, is approximately 316 plus 36 minus 30 days, or approximately 299 plus 25 minus 22 days, depending on the model variant. An event lasting roughly a year. For comparison, typical microlensing events in the galactic bulge last days to weeks. An event lasting nearly a year implies a massive or nearby lens, or both. Howell and Wierzykowski's analysis incorporates microlensing parallax effects, the distortion of the light curve shape caused by the Earth's orbital motion around the Sun during the year-long event, and applies Milky Way galaxy priors through an open-source inference routine they developed called dark lens code. The routine integrates over the possible lens positions and velocities given the galaxy's known stellar density, dark matter distribution, and kinematic structure. The result is not a single mass and distance, but a posterior probability distribution, a range of lens parameters weighted by how likely each configuration is given both the microlensing data and the galaxy model. The analysis yields two distinct lens mass solutions, two peaks in the posterior distribution corresponding to two geometrically distinct configurations. 4.9 plus 5.4 minus 2.3 solar masses at a distance of 1.14 plus 0.75 minus 0.57 kiloparsecs, or 11.1 plus 10.3 minus 4.7 solar masses at a distance of 1.31 plus 0.80 minus 0.60 kiloparsecs. The uncertainties are large, reflecting the inherent degeneracies in microlensing, where the same light curve can be produced by different combinations of mass, distance, and velocity. But the blended light analysis provides an additional constraint. The amount of light at the position of the event that is not attributable to the source star is too faint to be consistent with a main sequence star massive enough to produce the observed lensing. The lens is likely a dark remnant, a black hole or a neutron star drifting through the disk of the Milky Way, detected not by any light it emits, but by the way it bends the light of a star behind it. The dual-mass solutions illustrate a key limitation of photometric-only microlensing. Without an astrometric measurement of the Einstein radius, which Gaia can provide for events with strong enough signals, but which is difficult for events near Gaia's sensitivity threshold, the lens mass cannot be determined uniquely. The parallax measurement constrains a combination of mass and distance, but the individual values remain degenerate. This is why the HST astrometric follow-up of events like OGLE 2011 BLG 462 is so valuable. The astrometric measurement of theta sub E breaks the degeneracy and yields a unique mass. For events that lack astrometric follow-up, the mass remains ambiguous, and dark lens candidate is a more accurate description than confirmed black hole. Kailash Sahu and collaborators provided a more definitive case, and one that illustrates both the power and the fragility of astrometric microlensing as a tool for weighing invisible objects. Using the Hubble Space Telescope for astrometric microlensing follow-up of the event OGLE 2011 BLG 462, a long-duration microlensing event first detected by the OGLE survey toward the galactic bulge, Sahu's team measured the astrometric deflection of the source star over multiple HST epochs spread across several years. The approach requires extraordinary precision. The positional shift of the source star, produced by the gravitational field of the invisible lens, must be measured against the background of thousands of other stars in a crowded bulge field, with each frame requiring careful point spread function subtraction and astrometric calibration. The updated analysis, incorporating additional HST epochs beyond the initial publication, reports a lens mass of 7.15 plus or minus 0.83 solar masses at a distance of 1.52 plus or minus 0.15 kiloparsecs. with a relative velocity of 51.1 plus or minus 7.5 kilometers per second. No companion was detected in the searched ranges, no binary partner, no surrounding nebulosity, no X-ray emission. The lens is consistent with an isolated black hole, a single dark compact object approximately 7 times the mass of the Sun, drifting through the Milky Way at 51 kilometers per second, approximately 5,000 light-years from Earth. At that velocity, the black hole covers roughly the distance from Earth to Jupiter every year. It emits nothing. It accretes nothing detectable. It was found because it bent the light of a star behind it. A counter-narrative must be noted because it reveals the model dependence inherent in single-event astrometric microlensing claims. C.Y. Lamb, working independently in 2022, presented an alternative interpretation for the same event, OGLE 2011, BLG 462, arguing that the lens mass is consistent with a lower range of 1.6 to 4.4 solar masses. This mass range straddles the so-called mass gap between the heaviest known neutron stars, approximately 2 to 2.5 solar masses, and the lightest confidently identified black holes, approximately 5 solar masses. In Lamb's analysis, the lens could be a massive neutron star or a low-mass black hole, a mass gap object, rather than a definitive stellar mass black hole. The disagreement between Sahu's and Lamb's analyses arises from differences in how crowded field photometry is handled, specifically how blended light from nearby stars is modeled and subtracted. In dense, stellar fields like the galactic bulge, multiple stars contribute light within a single resolution element. The amount of blended light affects the inferred lensing amplification, which in turn affects the inferred Einstein radius and the derived lens mass. Sahu's later analysis, with additional HST epochs and more refined PSF subtraction, favors the higher mass black hole interpretation. But the earlier disagreement, published, peer-reviewed, and based on the same underlying data, remains a cautionary example. Any individual microlensing claim of a dark lens must be evaluated against the systematics of crowding, blending, and model priors. The field has matured enough to identify these systematics explicitly. It has not yet eliminated them. Think about what these detections represent. An isolated black hole, 7 solar masses, 5,000 light-years away, moving at 51 kilometers per second. It emits no light. It accretes nothing detectable. It was found because it bent the light of a star behind it, a distortion measured by the most precise astrometric instruments ever built. Without microlensing, this object would be completely invisible. It would be one of millions, perhaps hundreds of millions, of similar objects drifting through the Milky Way's disk and halo, remnants of massive stars that lived and died billions of years ago, leaving behind compact cores that interact with their surroundings only through gravity. The distance, 1.52 kiloparsecs, roughly 5,000 light-years, places this object within the Milky Way's disk, relatively nearby in galactic terms. At 51 kilometers per second, relative to the surrounding stellar field, the black hole crosses roughly 52 light-years per million years. It has been drifting since the massive star that produced it exhausted its fuel and collapsed, an event that occurred billions of years ago, given the ages of typical disk stellar populations. In the time since its formation, this single black hole has traversed tens of thousands of light-years through the galaxy, interacting gravitationally with everything it passes, but emitting nothing and accreting nothing visible. It is a gravitational influence without an electromagnetic signature, mass without light. The detection required the alignment of two unlikely conditions. The black hole had to pass close enough to the line of sight to a background star to produce a measurable lensing signal, and a survey had to be operating at the right time and in the right field to catch the event. OGLE provided the initial photometric detection. HST provided the astrometric follow-up over multiple years. The combined effort, ground-based monitoring plus space-based precision astrometry, is the current state of the art for weighing individual dark, compact objects. It works, but it is slow, expensive, and inherently limited by the random geometry of lens source alignments. Each detection is a chance event. The population must be inferred from the rate of chance events, not from a systematic census. The microlensing parallax relation provides the mathematical framework for extracting lens mass from these observations. M equals theta sub e divided by kappa times pi sub e, where pi sub e equals pi sub rel divided by theta sub e. Kappa is a constant. Pi sub e is the microlensing parallax, a quantity that encodes the curvature of the lensing light curve due to the observer's orbital motion around the Sun. Combining the astrometric measurement of theta sub e with the photometric or parallax measurement of pi sub e breaks the degeneracies inherent in microlensing and yields a mass and distance for the lens. This is the technique that turns an invisible object into a measured quantity, a mass, a distance, a velocity. This brings us to the population-level question: how many of these objects are there? And here, the evidence comes not from detections, but from non-detections. Przemek Mróz and Andrzej Udalski, leading the OGLE collaboration at the University of Warsaw, have spent more than 2 decades monitoring stellar fields toward the Large Magellanic Cloud, a satellite galaxy of the Milky Way, located approximately 160,000 light-years away. The monitoring program, OGLE-3, from 2001 to 2009, OGLE-4 from 2010 to 2020, observed approximately 78.7 million source stars in the direction of the LMC over a baseline of nearly 20 years. The logic is direct and worth stating with care, because this is one of the most powerful examples in modern astrophysics of the scientific value of a null result. If the Milky Way's dark matter halo contains a large population of compact objects, stellar mass black holes, intermediate mass black holes, or primordial black holes, then these objects, moving through the halo on orbits determined by the Milky Way's gravitational potential, should occasionally pass close to the line of sight between Earth and an LMC star. When they do, the gravitational lensing effect brightens the LMC star temporarily. The duration of the brightening depends on the lens mass. More massive lenses produce longer events because they have larger Einstein radii and therefore larger cross-sections for lensing. For halo compact objects in the stellar mass to intermediate mass range, 1 to hundreds of solar masses, the expected event timescales are months to years. A 10 solar mass halo lens at a distance of several kiloparsecs, moving at typical halo velocities of 200 to 300 kilometers per second, would produce a lensing event lasting approximately 1 to 2 years. A 100 solar mass lens would produce an event lasting several years. The microlensing optical depth, tau, quantifies the probability that any given source star is microlensed at any given time. It depends on the total mass in compact lenses along the line of sight and on the geometry. The event rate, gamma, counts the number of microlensing events per year per monitored star. Both quantities are calculable from models of the halo compact object population, and both are directly measurable from the observed microlensing events. OGLE found 16 microlensing events toward the LMC over the 20-year baseline. All 16 had timescales shorter than 1 year. None had timescales longer than 1 year. This is the critical finding. The measured optical depth is tau equals 0.121 plus or minus 0.037 times 10 to the negative 7th. The measured event rate is gamma equals 0.74 plus or minus 0.25 times 10 to the negative 7th per year per star. Both values are consistent with the expected lensing from known stellar populations, disk stars in the Milky Way, and stars within the LMC itself, acting as lenses for other LMC stars. Neither requires a large population of dark halo compact objects. The observed events are explained entirely by ordinary stars. No dark halo population is needed. The absence of long timescale events is where the constraint becomes powerful. If the Milky Way halo contained a large population of compact objects with masses of 10 to 100 solar masses, the 20-year OGLE baseline, monitoring 78.7 million stars continuously, should have detected events lasting 1 to several years. The expected number of such events, given the monitored source count and the survey duration, is large enough that even a modest halo fraction would produce detectable events. None were found. 0. In 20 years. Among 78.7 million stars. The non-detection translates into strict upper limits on the fraction of dark matter that can consist of compact objects. If the Milky Way halo contained a large population of compact objects with masses of 10 to 100 solar masses, the 20-year OGLE baseline should have detected events lasting 1 to several years. None were found. The non-detection translates into strict upper limits on the fraction of dark matter that can consist of compact objects. Objects with masses between 1.8 times 10 to the negative 4th and 6.3 solar masses cannot constitute more than 1% of the dark matter. Objects with masses between 1.3 times 10 to the negative 5th and 860 solar masses cannot constitute more than 10%. A separate OGLE high-cadence campaign, conducted from October 2022 to May 2024, monitored approximately 35 million source stars toward the Magellanic Clouds at high time resolution. This campaign targeted short timescale events, the signature of planetary mass primordial black holes that some recent proposals had invoked to explain excess short timescale events observed toward the galactic bulge. The result? No short timescale events were detected. Primordial black holes with masses between 1.4 times 10 to the negative 8th and 0.013. Solar masses can constitute at most 1% of the dark matter. Before we continue, consider what this means. Take a moment. The strongest constraints on primordial black holes as a dark matter component come from 20 years of watching and finding nothing. The decisive evidence is absence. Tens of millions of stars monitored for 2 decades. If massive compact objects populated the halo in large numbers, their gravitational signatures would have appeared in the OGLE data as sustained brightenings of LMC stars lasting months to years. They did not appear. The absence is not ambiguous. It is quantitative. It excludes specific mass ranges at specific confidence levels. The population census is conducted by absence. This is a detection method that inverts the normal logic of observational science. Normally, you discover something by seeing it. Here you constrain something by not seeing it. The OGLE survey's power lies not in the 16 events it detected, but in the vast number of events it should have detected if massive halo lenses were abundant, and did not. The non-detection, applied to tens of millions of source stars over 20 years, becomes an exclusion. The exclusion, applied to the known halo mass, becomes a population limit. The population limit, even at the 1% level, still corresponds to enormous absolute numbers, because the halo is enormous. A simple calculation anchors the population estimates. The number of primordial black holes in the Milky Way halo can be estimated from the identity n sub pbh equals f sub pbh times m sub halo, divided by m sub pbh. N sub pbh is the number of primordial black holes. F sub pbh is the fraction of the halo mass consisting of primordial black holes. M sub halo is the total halo mass. M sub pbh is the mass of each primordial black hole. Using the Gaia-based Milky Way halo mass estimate from Marius Kautun and collaborators, M sub 200 dm, approximately 0.97 times 10 to the 12 solar masses, with a local dark matter density of approximately 0.33 giga-electronvolts per cubic centimeter, even a 1% fraction corresponds to roughly 10 to the 10 solar masses of primordial black holes. If each has a mass of 1 solar mass, that is 10 billion objects. If each has a mass of 10 solar masses, that is 1 billion objects. Small fractions of halo mass map to enormous absolute populations. The OGLE limits constrain the fraction. The arithmetic converts fractions into counts. Himanshu Verma and Vikram Rentala published a dedicated Gaia Astrometric microlensing sensitivity forecast for primordial black holes. Their analysis projects Gaia's sensitivity across a wide PBH mass range, approximately 0.4 to 50 million solar masses, with peak sensitivity near 10 solar masses. Under low background assumptions, they project that Gaia could exclude PBH dark matter fractions as low as approximately 3 times 10 to the -4th, 300ths of 1%. The constraint would be notable if achieved, but the strongest current claims rely on assumptions about astrophysical backgrounds that are not yet fully validated. The OGLE constraints, based on direct non-detections rather than forecasts, remain among the most stringent in several key mass windows. Gaia Data Release 3-based astrometric microlensing prediction papers report approximately 4,500 predicted AML events with signals exceeding 0.1 milliarc seconds between the years 2010 and 2070. These predictions span the full range of lens types, not just black holes, but also neutron stars, white dwarfs, and ordinary stars. The black hole subset is a fraction of the total, but even a small fraction of 4,500 events represents dozens to hundreds of potential dark lens detections over the coming decades. The pipeline is maturing. The data is accumulating. The question of how many invisible black holes drift through the galaxy is transitioning from theoretical estimate to observational constraint. We can measure the distances, calculate the masses, map the structures. But what set all of this in motion, and why these laws and not others, remains unanswered. Let us now assemble the full picture, the forensic reconstruction of what the evidence tells us about the population of rogue black holes in the observable universe. The evidence comes in 3 categories, and each category tells a different part of the story. The first category is direct observation of an ejected supermassive black hole, the 200,000 light-year streak. This is a single object, observed at a single redshift, in a single galaxy's circumgalactic medium. The observation tells us that SMBH ejection is physically possible and that the resulting wake can be detected when conditions are favorable, when the ejected black hole encounters sufficiently dense circumgalactic gas to drive observable shocks and trigger star formation. But the observation is at redshift 0.964, we are seeing the system as it appeared roughly 7.5 billion years ago. The speed of light delay means we cannot observe the system in its current state. We are reconstructing a past event from its fossil record, the light that left the system billions of years before humans built telescopes. The JWST conformation, the kinematic discontinuity, the refined velocity of 954 kilometers per second, the mass floor of 10 million solar masses strengthens the wake interpretation, but does not close the debate. Sanchez Almeida's edge-on-galaxy alternative has not been definitively excluded. The observational arc, Hubble imaging to Keck spectroscopy to JWST integral field spectroscopy, represents the most thorough investigation of a single astrophysical feature that could be a runaway SMBH. But most thorough is not conclusive. The evidence converges on the wake interpretation. The alternative remains in play. This is how science at the frontier operates, not with definitive verdicts, but with accumulating weights of evidence. The second category is simulation-based population estimates. Galaxy mergers produce triple SMBH systems at a rate quantified by Satish, Blecher, and Kelly. Approximately 6% of massive black hole binaries form triples at parsec scales. Slingshots and recoil kicks eject some fraction of these. Romulus and Astrid simulations predict large populations of wandering black holes, hundreds to thousands per massive halo, accumulated over billions of years of galaxy assembly. These predictions are quantitative but model-dependent. The triple fractions depend on how binary hardening is modeled, on the subgrid physics that governs unresolved dynamics. The spin orientations that determine recoil velocities are uncertain for real SMBH binaries. The predictions are the best available. They are not definitive. Even with these caveats, the qualitative conclusion is sound. Galaxy mergers should produce a large population of displaced and ejected black holes over cosmic time. The specific numbers, how many per galaxy, what fraction are ejected versus merely displaced, what their current distribution looks like, remain uncertain at the factor of several level. But the existence of the population is a prediction of standard gravitational dynamics applied to known merger rates. The physics that produces rogue black holes is the same physics that produces galaxy growth. One cannot occur without the other. The third category is microlensing-based detection and constraint. Individual detections, Sahu's 7.15 solar mass isolated black hole, the Gaia 18AJZ candidate, confirm that dark stellar mass compact objects exist in the Milky Way's disk and can be detected through astrometric microlensing. These individual detections cannot, by themselves, determine the total population. A single detection tells you that the population is not zero. It does not tell you how large the population is. Converting sparse detections into a reliable galaxy-wide inventory requires understanding the selection function, the probability that a given black hole at a given distance and velocity would produce a detectable AML event during a given survey, and this selection function is still being calibrated. The OGLE non-detections provide the complementary constraint, not how many did we find, but how many can we exclude. The 20-year LMC monitoring program excludes compact objects across a wide mass range as a major dark matter component. The constraints are quantitative and specific. Objects with masses between 1.8 times 10 to the -4th and 6.3 solar masses cannot exceed 1% of the dark matter. Objects between 1.3 times 10 to the -5th and 860 solar masses cannot exceed 10%. The high-cadence Magellanic Clouds campaign further excludes planetary mass primordial black holes at the 1% level. The limitations must be stated clearly. The OGLE constraints apply to compact objects in the Milky Way's dark matter halo, objects on halo orbits that cross the line of sight to the LMC. They do not directly constrain the population of stellar mass black holes in the Milky Way's disk, which have different spatial distributions and kinematics. They do not constrain primordial black holes in mass windows outside the survey's sensitivity range, and they assume a monochromatic mass function, that all compact objects have the same mass. If the actual mass distribution is broad or clustered, the constraints can shift. The instrumental cadence of Gaia also limits what can be detected. AML, events that peak outside Gaia's operational window, or events that are too short for Gaia's scanning cadence to sample adequately, may be missed. Pipeline development papers explicitly test these recovery degradation effects and report that mass recovery is reliable for lens masses of approximately 1 to 20 solar masses with sufficiently strong signals. But degradation is real for events at the edges of the sensitivity range. Stellar mass black holes, the remnants of massive stars, drift through the Milky Way in numbers that remain poorly constrained but are expected to be large. Population synthesis models, which track the birth, mass loss, and death of stellar populations over the galaxy's 13-billion-year history, predict tens of millions to hundreds of millions of isolated black holes in the galaxy. These are not primordial. They are not exotic. They are the expected end products of massive stellar mass loss accumulated over billions of years. Most formed from stars more massive than approximately 20 to 25 solar masses that exhausted their nuclear fuel, collapsed, and left behind compact remnants between roughly 3 and 50 solar masses. Most received natal kicks during the supernova or collapse that formed them, kicks that displaced them from their birth sites and set them drifting through the galaxy on orbits that may never return them to their origins. Most are invisible. Most will remain invisible. Astrometric microlensing offers the only current method for detecting and weighing them individually, one centroid shift at a time. The Gaia DR3-based prediction of approximately 4,500 AML events, with signals exceeding 0.1 milliarc seconds between 2010 and 2070, represents the discovery space. The black hole subset is a fraction of the total. But even a small fraction of 4,500 events, if the events can be identified, characterized, and their lens masses measured, would transform our understanding of the galactic compact object population from theoretical estimate to observational census. The near-term frontier is Gaia Data Release 4, expected December 2026, which will roughly double the time baseline relative to DR3. A doubled baseline improves astrometric solutions, the precision of star positions and motions, and should improve the detection and characterization of AML events, especially long-duration events produced by massive lenses. The long-term frontier is DR5, expected no earlier than 2030, which will incorporate the full mission dataset. Each release represents a step toward the goal of a systematic census of dark, compact objects in the Milky Way. conducted not through emitted light, but through bent light. Some questions may simply be beyond what science alone can address. The equations describe the lensing. The simulations predict the populations. The surveys constrain the fractions. But the question of why the laws of gravity produce compact objects that are simultaneously the most extreme distortions of space-time and the most invisible inhabitants of the galaxy, objects that can only be found by the light they bend, not the light they emit, is not a question physics answers. Physics describes the mechanism. The mechanism produces the population. The population drifts, unseen, through the same galaxy we inhabit. We share a gravitational potential with objects we cannot see, cannot detect by any emission, and can only infer through the fleeting distortions they impose on the light of distant stars. The millions in the title is defensible, but it requires precision. For stellar mass remnants roaming the Milky Way, objects formed from the deaths of massive stars over billions of years, population synthesis models predict tens of millions to hundreds of millions of isolated black holes in the galaxy. These are the expected end products of massive stellar mass loss accumulated over 13 billion years of galactic history. For wandering supermassive and intermediate mass black holes, objects displaced by tidal disruption, inefficient dynamical friction, or multi-body encounters, the simulations predict hundreds to thousands per massive halo, depending on mass and merger history. For primordial black holes, hypothetical objects formed in the very early universe, the OGLE constraints limit their abundance to no more than 1 to 10% of the dark matter across broad mass ranges, though even 1% of a trillion solar mass halo maps to billions of solar masses in compact objects. The parameter space for primordial black holes is shrinking, not expanding, with each survey extension and each non-detection. Rogue black holes. The 200,000 light-year wake of a runaway supermassive black hole imaged by Hubble and confirmed by JWST at a velocity of 954 kilometers per second. The three-body slingshot and gravitational-wave recoil mechanisms that produce ejections from galaxy nuclei. Astrometric microlensing, centroid shift detection of dark lenses using Gaia and HST. OGLE's 20-year LMC monitoring and its quantitative exclusion of primordial black hole dark matter across broad mass ranges. The SAHU measurement of a 7.15 solar mass isolated black hole at 1.52 kiloparsecs. The Howell and Wierzykowski analysis of Gaia 18AJZ with its dual dark remnant mass solutions. The Illustris and Romulus simulations predicting triple fractions and wandering populations. The Astrid prediction of hundreds of wandering intermediate mass black holes per galaxy at high redshift. The Verma and Rentala forecast of Gaia's PBH sensitivity. The OGLE high cadence campaign excluding planetary mass primordial black holes. The evidence file is thick. The population is large. The objects are invisible. The detection methods are indirect. The constraints are tightening. And the galaxy, our galaxy, hosts millions of compact objects that emit no light, accrete no detectable matter, and interact with their surroundings only through the curvature of space-time. They are there. They are drifting. They are dark. Not tragic, not triumphant, just present. Good night.